I have a few things pulled up on my computer that I'm going to attempt to share as like a green screen or something. So I promised last night, towards the end of the live, we talked about neutrinos. Several people that joined were interested in that topic. We started off the live last night talking about neutron stars and pulsars, and how, pulsars were discovered, and at first they didn't know that they were connected with neutron stars, and they came up with certain candidates of what it could be, and eventually hello, by the way, thank you so much for joining and liking the live. Hello, welcome. Thank you so much for being here. Please do say hi in the chat, and say hello, introduce yourself. Thank you so much for being here. But anyways, to recap, people were not sure when they saw the pulsars signature that those were indeed, in fact, associated with neutron stars, but neutron stars were the only candidates that kind of lasted or survived what all you needed to be in order to satisfy being a pulsar, because pulsars were very interesting, very sort of extreme signatures that we were seeing. So we kind of got into the details of that last night. And then I was going to wrap up, but some people joined and asked questions about neutrinos. And so I ended up talking about neutrinos, which is a type of lepton. It is in the same family as the electron actually, but they're very different particles. Although they belong to the same family of particles, which is called leptons, neutrinos don't have a charge, they don't interact electromagnetically, and they in fact only interact weakly or with the weak force, the weak nuclear force. And so sorry, I'm checking out the buttons as usual and making sure that all the settings are set, which I probably have to do more of in a bit on this direction as well. But basically, we were chatting about the neutrinos, and this may be a particle that people are still a little bit less familiar with, even though it's been around for a while. And just because it is so weakly interacting, because it's the weak nuclear force, is the only type of force that it interacts with. It tends to be very introverted. It does not interact with the other particles as much, because it would only interact via that weak nuclear force. And so they actually have the potential to be very good messengers of astronomy. If you are able to see neutrinos from a certain direction, from a certain source, astrophysical source or whatever, something like that, then they could be coming from far, far away, undisturbed by other interactions, because they are weakly interacting. But at the same time, the same thing that makes them such a reliable astrophysical messenger is also the same thing that makes them very hard to detect. So we were talking about all of that stuff last night towards the end. I don't know if the same people will join tonight that I was hoping to talk to about this, but also I can talk to anybody about this. So if you're going to be joining, thank you so much. I will say once again, welcome everybody to the chat, to the live. I hope that many of you join, old people, new friends, old friends. Please do like, share, subscribe if you're joining, and hopefully the audio works well and everything goes well. And I've got some other books around here as well. We have been referencing the modern astrophysics book. It's called An Introduction to Modern Astrophysics. Oh my gosh, I'm dropping things all around me as well for references. Plus, I have some slides pulled up from my thesis, but I'm trying to find a way to actually share them as a green screen and whatnot. So that's what we're doing tonight. And if you're joining, thank you so much. And I hope that you do join. And let me share the live. And if it's a quiet one, then that's okay. I will point out a few things and go to bed. But if people join, then I'm happy to stay on and chat for a bit and all of that stuff. So I hope that you say hi in the chat. Ooh, good. I called it the neutrino chat. I was checking, what did I call this live? Neutrino chat. Okay, good. Now, let me share it. Let me share it to my channel. So lately, since yesterday I noticed, since yesterday I've noticed that the live streams have been a little weird. I believe that YouTube actually has an issue right now with live streams, and it's been not letting me always comment and share and things like that in my own lives. So there might be something of an issue going on, and if that's the case, then at least I hope that you see this as a video upload later on and put something in the comments. Say hi in the chat if you're joining, because I'm not sure things are working or not. And then also please do say hi in the comments and leave a comment later on if you're seeing this as a video upload or whenever you see this. Thank you so much. Let me go over to my laptop and see if things are looking mostly normal. I do see that things are a little bit different looking tonight. So as in when I saw it from my other phone, it wasn't letting me share it, which is a bummer. Quite a bummer. What? Sorry, I'm still looking at it from my laptop. What on earth is going on? Things just look kind of different. I think there is an issue going on maybe with the live streams right now. Oh, I see. Did I think I did this wrong. There is a setting that that's a little bit not correct. Let me make sure that that's not the case. Hello everybody, thank you so much for joining. How are you doing? Please do like, share, subscribe, say something in the chat, say hi in the chat so I know you're here, and give me just a moment to get things set up on my laptop. And I'm going to be trying to share a slide from my work so that we can talk about neutrinos. And also if you're joining and, oh, you know what? I think I accidentally set something. Oh, yeah. There we go. I think I accidentally set something for kids only. And I messed it. It's not letting people comment or something. One second, sorry. If you're not able to comment, that could be because I set it accidentally to kids only, which is not something I have done before. Are the comments working now? Oh my gosh. Why is chats disabled? I don't mean to do that. Sorry guys, give me one more second. Let me try to figure this out. Why is age restriction? No, I don't want. No, it's not made for kids. I don't know what on earth is happening. Sometimes some buttons get oh. I see. Save. If I refresh it, is the chat working now? I accidentally had made it kids only. Not that I meant to press such a button, but public. Okay. I hope that the chat is working. Okay. Can you guys see me and say stuff in the chat? Oh yes. Is it working? Is that me? Neutrino chat? I'm so confused even by myself, to be honest. and whatnot. But hi, if you're here, please do like, share, and subscribe. Okay, I can't see my own comments either, turns out, so, you know, oh well. But okay, so yeah, last night we were talking about, chat is working now. Oh my gosh, Pranay, hi. Thank you. Why is it not showing me? Why is it top fans? Pranay. Hi, Pranay. How are you doing? It's not showing me. Agasio! Agasio, how are you? Hello, my friend. Hello, my friends. So you can hear me, right? You can hear me, you can see me, you can see the chat. Adam! Here I am, Adam. We can talk about neutrinos. That's why I'm here. So Acacio and Pranay, well, Acacio, I think you missed last night, but Pranay was here and Adam was here, and we were talking about the neutron stars, and then pulsars, and then we also talked about neutrinos. So neutrino is a different particle than the neutron. It's not the same, but they have sort of a similar sounding name, so I wanted to clarify. But neutrinos are in the same family of particles as the electrons, which is the family is called leptons, and we will talk about that tonight. So Adam, do you have more questions to start off, or I'm gonna try to share the slide that I promised and things like that, and we will keep going. Pranay is asking me my age. Oh my gosh. My goodness, I was screaming loud, not chatting aloud. Yes. Gosh, that would be quite sad. Acacio, how have you been? How are you doing? Okay, so now that I know that the chat is working, which was very weird, let me take a screen. Let me do this. Let me do the thing where I do a thing, okay? Let me share with you a slide which I have been meaning to show you, and that will give you some visual, okay? Now, where is my, I need to share, I need to first, oh, you know what? Let me put this, I have to save it as a photo. Sorry. Give me 1 second. So basically, Adam had asked about neutrinos. Adam, do you have any more questions? Adam says, can you talk about the flavors more? I thought you were joking, and then I saw later they're actually called leptonic flavors. Yeah, I wasn't joking. The neutrinos do have flavors. They are sort of named after the same particle as the other leptons. So, okay, the leptons are electrons, muons, and taus, okay? So, so once again, the leptons are electrons, muons, and taus, and also the neutrinos. So let me get to that. But the first sort of generation of leptons is the electron, muon, and tau, with the mass increasing in that order. And also all of these particles that I just now mentioned have different lifetimes. They decay at different times, okay? They're not all equally stable. So of course, you will come across more stable particles more often in nature. So for example, electron is something we know and love because electron exists in nature as a stable particle. Muon will decay, taus will decay after a short amount of time once they're made, and so you might not come across one very easily, but of course we do come across them, especially when we do experiments, and there are different signatures of each one, and sort of making one, even if it lasts for a brief period of time, is worth it to say prove something out, etc., or get the signature of something. Okay. Hi, Clinton. Hi, Stephen. Hi, Stephen. Sky Reading. Hello. And then Clinton Emily says hi. Hi, Emily. Hi, Clinton. So electrons, muons, and taus, those are the sort of the first generations. And then we are, sorry, those are the leptons and their generations in that first row that we generally look at in particle physics. And then there are neutrinos, and there's a flavor per per lepton, basically. So there's an electron neutrino, a muon neutrino, and a tau neutrino. So those are the three flavors of the neutrino. And then each of the leptons also has an antiparticle. So there is an electron anti-neutrino, a muon anti-neutrino, and a tau anti-neutrino, and whatnot. So those are the three generations or the three flavors of the neutrinos. And again, the neutrinos too have different masses for the different flavors, but they're all neutrinos are very low mass. And so for the longest time, people actually thought that they might not have a mass. It was difficult to measure the mass, and even now the masses are known, I believe, to some error bars. Okay, so that's the situation with the flavors. The stuff that I was going to share with you is not going too much into the detail of the flavors, as it is just kind of more broadly how neutrinos play a role in astrophysics. So basically, this whole discussion of the leptons, the lepton family, electrons, muons, taus, a lot of details about each of those particles, the neutrinos, the flavors of neutrinos. This is more of a particle physics discussion. When you sort of cross-section particle physics with how it plays a role in astrophysics, we call that particle astrophysics. That's my background. And so I was more looking at neutrinos in terms of what can they do / what can they mean in terms of astrophysics findings and astrophysics sources and things like that. So it's really in that intersection that we were more interested in. So we might not be so interested in the details of the flavors and stuff, but at the same time, the devil is in the detail, right? So to some extent, the flavors do matter, because depending on which flavor of neutrino, it might make a different, what we call secondary particle. Hi, B. No, you're fine. We just kind of started. So good thing that Adam has brought up the flavors and the leptonic family. So let me say hi to everybody. I have to look here because apparently I can't see the comments and the chat on my phone over here, which usually I can see my screen and say hi to everyone, but apparently I can't. So hi Pranay, hello Acacio, hola amigo, how are you doing? ¿Cómo estás? Adam, Clinton, Emily, Stephen, B, how are you doing, everybody? So I'm glad that Adam asked about the leptonic flavors, because it's good to think about them as in the other leptons, electrons, muons, and taus, because depending on which neutrino, so I was talking about how we basically have to detect the signature of a neutrino interacting in some kind of material. Because neutrinos are extremely elusive particles, it's very difficult to detect them. You have to be quite, you have to develop the craft of detecting them and a strategy to detect them. And generally it involves lots of a detection volume or a detection medium or a detection material. This is generally a dielectric medium, okay? So we are basically at this point hoping that the neutrino will interact with that dielectric medium, and the more you have of that dielectric medium, the better. Then the neutrino has hopefully lots of chances to interact, or you just hope to look for such interactions for a very, very long time, so that again you increase your probabilities of actually seeing one interact, that is. And then the signature from that interaction is what we are ready to then detect with our detectors, and you design your detectors accordingly, okay? So for example, if you are looking for the radio signature of a neutrino's interaction, you would be ready with your radio setup, your RF setup, radio frequency, radio antennas, you know, signal processing, all of the radio stuff would be ready. And that's the project that I worked on. It was a radio frequency project. The signal of that neutrino interaction would be in radio waves. And so you have to make sure that your instrument is sensitive to that. So I essentially worked on an RF instrument for this work. Then there are people who look for the optical signature of neutrinos interacting. Those people's instrument is going to be totally different. They will not look with radio antennas and radio instruments, but they will look with, say, photomultiplier tubes, right? So that's actually a very common one. So somebody asked, B asked, what's the medium you most want to experiment with right now? So I like ice. So we went to Antarctica to do this experiment because Antarctica is mostly ice. It is the only continent on this planet anyways that is 99 point something percent, I think 99% ice, and it has a little bit of rock. Fun fact, the little bit of rock of Antarctica is because of volcanoes, volcanic rock, and just mostly all ice. And so because of Antarctica having so much ice, I mean, Greenland was the other option in the northern hemisphere, but I think there were lots of different reasons, and one of them was logistics. But also it's good to sort of have your instruments covering multiple parts of the sky. So say there's a lot going on in the northern hemisphere, then you want something in the southern hemisphere so that you can see the southern sky and things like that. And well, I mean, some neutrinos go all the way through, so then that affects your noise and what you have to deal with and blah blah blah. But pretty much the electrons, or not the electrons, the neutrinos that my experiment was interested in were high, very high energy, ultra high energy neutrinos. So they're not expected to go all the way through the Earth as easily, because remember how I mentioned that when the neutrino has higher energy, it actually has a greater cross-section for interaction, so it will interact more. So if you have a very high energy neutrino, it may actually interact in the Earth. And turns out, because of the geometry reasons of what we were sensitive to, we would be basically be looking at kind of like Earth skimming neutrinos and not neutrinos that would be going all the way through the Earth, blah, blah, blah. So basically we were looking at the southern sky by being in Antarctica. But yeah, so depending on, so I'm still answering the question about the medium. So I should say that you want whatever medium it is, hopefully you have it in abundance. Hopefully you have a lot, because if you don't have a lot, or if you don't have a lot instrumented, then you're gonna have lesser chance of seeing the neutrino, right? Because you could have a lot of ice, but let's say you have instruments set up only to look at a certain part of the ice. For example, ice cube is a cubic kilometer volume ice experiment, also in Antarctica. They're at the South Pole, and they just look at literally a cube of ice. That's why they're called ice cube. So they look at a cubic kilometer cube of ice, where they're also looking for neutrinos to interact in the ice and pick up the signature of that, but they are in an optical wavelength experiment mainly. So they are looking for high energy neutrinos that are sort of PeV range is the energy regime of that. So to instrument that volume takes, or to be sensitive to neutrinos of that energy, you can get away with maybe that volume of a detection medium. But if you want to be sensitive to even more high energy neutrinos, you might want to look at even bigger volumes. So things like that. So long story short, it really depends on which types of neutrinos you want to detect. For the very ultra high energy ones, I would say the ice is a really good medium, and Antarctica has a lot of it, and I love the continent. It's very beautiful there, very white, very hilly and ruggedy actually. And well, I was at McMurdo Station, so it's not like I've seen the whole continent. I've just seen a part of it. And I was there for, someone asked, how long were you in Antarctica? I was there for a few months. So I was there for the sort of the life cycle of the experiment, where we're like getting ready. Like I was we were deploying that year. So we had some test runs and some practice runs in actually Palestine, Texas, at the NASA Long Duration Balloon Facility there. So before you go to Antarctica, before you're ready to like ship your instruments and do the final, like the real thing, you have to do a hang test in the NASA facility in Texas. So we did that. I was there for that. Then we kept getting ready. You know, there's always things breaking, always things that still needs to be like prepared and assembled and put together for the instrument. And then then it gets shipped to the ice, to what we call the ice, which is Antarctica. And then we went to Antarctica. So shortly after my birthday in October is when I went, and I went through New Zealand, did the training in New Zealand to like know how to behave and know how to live in Antarctica, and then yeah, we got the instrument ready. I did a balloon borne experiment. So basically, these experiments to look for neutrinos are of various types. Either you can put the instrument in the ice directly to try to pick up on signatures of the neutrino interaction in the ice, or you can look from up above by hanging your detector from a gigantic balloon, and then you kind of survey the ice below you, and you can get to survey more of the ice, and that's how you actually instrument more volume. So stuff like that. Yes, so I'm getting kind of into the details of this, but yeah, that's pretty much how it works. And then so we went there. So at first you're just, you know, scrambling to get everything ready. Like there's still last minute like calibration tests and hardware things that you're doing to get everything ready. And then they give you a date. So believe it or not, the balloon is very important. It's not just a normal balloon. It's like the balloon is the size of like a football stadium. So this is not like a balloon that they let us lose. So NASA is the one that actually does the balloon, and they're balloon experts, because the balloon is this type of balloon mission is almost like a space mission. I mean, because the balloon takes the detector up to almost space, not quite, but it's way above where planes would fly and whatnot. It's like at a 40-kilometer altitude from the surface of the Earth is where my instrument went. So the stuff that I was working on for months and months and months, when I saw it like go up, it's surreal. It's like a really interesting feeling. Like it's like, wow, like my stuff went to almost space, you know, and now it has to work there. It's like, you know, like when you're working in the lab and something breaks, you can fix it, or you can at least try to fix it and do something. But like when you're putting something to fly, either in space or close to space, then you really hope that you've done a good job, because now you can't do anything. It's up there, and hopefully it's working and collecting the data and doing the things that you wanted it to do, because it's up there at 40 kilometers altitude from the Earth's surface for like a month. So balloon missions generally fly for order of like a month or so. Space missions, of course, can be in orbit a lot longer, but they're also a lot more expensive. So space missions, like things that you put actual in orbit around the Earth, are very expensive. You need something to put the thing in space, right? So that takes a lot of fuel, et cetera, et cetera. So that that can be very expensive. So whereas a space mission could be in the billions of dollars, you can do a balloon mission for like in the millions of dollars. So literally like M versus B, you know. So like 3 orders of magnitude less expensive. So our balloon mission was almost like a space mission, but not quite. And so it's a lot cheaper. NASA helps us to deploy the balloon. The balloon is filled with helium. So it's not a cheap balloon. It's like a special balloon, and it's very weather dependent as to, so any launch is very very finicky. Like you think you're going to launch today and then you can't because of something. So, I mean, the balloon launch was canceled. It's called a scrub. It's like you go out there, you're like, okay, we're going to get ready. And like we barely slept. And you think that you're going to launch today. And then you get there and like the wind is a little bit too, rough or something, and you can't launch. Like the balloon missions are extremely finicky. Sometimes people miss their launch window because the weather is so, like they just never got a good weather day for the balloon to, like, because the balloon is so gigantic, like they can't just if the launch goes here and there, then your whole thing is messed up. So that's why they have to be careful. How does it come down? So there is a way to basically crash it gently. And so there's a little thing you can do to eject the balloon, and then the instrument parachutes down to the ice. And then there is some people who go to rescue the instrument. And it's called a rescue mission of the instrument, and the balloon is just lying there too, and you can't really reuse the balloon. So pretty much they don't want to waste these balloons. Like they're a big deal, the balloons. So NASA, when and the people who go out there to help us with the balloon deployment, so we're doing the instrument, like the scientists are doing all of the instrument and the hardware and the data collection and the analysis and like all of that work, right? Like I was involved in all of the stages of this experiment. But the only part that we don't do ourselves is the balloon. That's because it takes a lot of special expertise, and like sort of the aerospace of the balloon, is like a whole thing. And so, and there's a special vehicle as well that that they use to hang the detector with the balloon, all that stuff. Actually, I have videos on this as well on YouTube. Actually, I think I have a video on YouTube where they're filling the balloon with helium and whatnot. So I have some videos as well. But anyway, can people also like, share, and subscribe, please? Some more likes would be great. But anyways, so when when you think that you're gonna launch and you go out there and you're actually not gonna launch, and this happens like 3, 4, 5 times, then one fine day, you think you're gonna launch and you're almost like expecting it to get scrubbed, but the NASA people actually take the balloon out. That's when we got really excited because they usually don't take the balloon out unless they think it's gonna be like for real. So it was an amazing day. Oh, and the thing that I was gonna mention earlier is that it's extremely weather dependent. So we actually utilize the polar vortex in Antarctica, in the polar regions, to make this balloon kind of orbit over the continent. So it literally goes around and over the continent in these sort of circular orbits. And the polar vortex helps it to do that. So depending on when the polar vortex sets in is when you want to be launching. Okay? So guess what? If the polar vortex is early, you should be launching early. If it's late, you have to launch late. So you're basically given a launch window based on whether you're ready or not. So the year when we launched, when my flight was going out or was launching, the polar vortex was early. And we had to get ready by like early December, which was really fun. It was a very hectic schedule. So there's that too. Adam is saying I have to head out. Okay, see you next time. B says, amazing story. Thank you. Hello. Hello, Tukesh. Hello, Virbhadra. Yes, so it's the austral summer. So it's summer there. It's 24/7 daylight during the summer there. So the sun never set. Literally, we would. So after the launch, we had more time. At that point, we were kind of monitoring, helping out with the post-launch and telemetry, and I actually had a very interesting role after the launch as well. But we started to have more fun after the launch, because up to the launch we were just working and working and working, and you know, it was very, very hectic. We didn't have a day off, etc. I think we had one day off because of the weather. There was like literally a storm, so you're like not allowed to go out and stuff like that. So but yeah, it's 24/7 daylight, the sun never sets, and we would like go to a bar, come out at 2 in the morning and the sun would still be up. There are like 2 or 3 bars in the station where I worked, McMurdo station. So it was a lot of fun. It was an experience of a nice of a lifetime. Oh yeah, so somebody asked, B said, did the instruments come back irradiated? I'm not sure what that means. Oh, I see. I thought you meant that. So, they're in a lot of protective casing. So they mostly come back fine, actually. So we do try to kind of rescue the instrument, bring it home again, work on it again, and use whatever parts we can again for the next flight. Because there are multiple flights of this experiment, so we do try to recover the instrument and bring it home and do more stuff. And the most important thing is that we have to. Hello, the bears. Where you been? I don't know. I've been around. So the biggest thing is that we have to collect the data. So the data is stored all on board, and once the landing happens, which is basically we gently crash the balloon, maybe not so gently crash the balloon, we basically have to go get the data drives and bring that home. Otherwise, the whole experiment was like basically you want to get the data drives, otherwise everything you collected is gone. Because we get some data down with telemetry, but most of it is stored on board. Okay, so now if you're joining, thank you for joining, and please do like, share, and subscribe. So, and let me answer your question. Veerbhadra Arya is saying, what experiment are you talking about? So I'm talking about ANITA, Antarctic Impulsive Transient Antenna. I don't actually think that I named it earlier, but that's the experiment I've been talking about. ANITA, we call it ANITA, Antarctic Impulsive Transient Antenna. And what do you do? So my background is in physics. I've been talking about physics on the channel, and I cover physics, astronomy, astrophysics, cosmology. We also show cats on this channel, and I'm a physicist. Not a physician, but a physicist. Okay. Now I want to do a thing where I share a visual with you guys, and let me see if that works. Give me a momento. Okay. Oh, yes. Yes, 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 yes. I think it's going along. How is everybody doing? Did it come? Did it get to my other? Because I'm hoping that if I share it, then I can green screen with it. Oh, oh, oh. Okay, let me do this now. Hello, I'm still here. Can you, okay, that was not too bad. Is my moderator still here? B, can you help answer some of these questions as well? And my name is Baji's mother. My name is Oindri. Okay, now let me see. Yes. Aha. Okay. Wait. Sorry. Does it let me? It's doing something, but I see. Okay. You know what? I gotta do this again. I see just neutrinos. Yeah, I know. I need to do the picture again. Hello, Veer. By the way, I'm also pursuing my research career. Okay, very nice. All right, sorry. Sorry. Give me one more second. Give me... Let me screenshot it. Can I? Okay, I see where it's cut. Okay, let me do that. Air drop. It keeps taking out my, okay, there. So now let me move out of the way a little bit. Okay, so I don't know if this is super helpful yet or not, because it's not letting me like move the picture. But I basically have, you know what? I don't think that's really helping much. Can you see anything? Let me just see. You have Antares. Okay, let me just talk about these couple of experiments. So basically, this slide was meant to show you, the energy regimes of some various experiments. I can't fit it all yet. I gotta redo the visual. But let me just point out a few things. So first of all, I have certain colors here, and those colors kind of mean that the experiments that are within those color boxes are sort of in the same, similar energy regime. So the green boxes that says one of them is Antares, Antares, see Antares right here, or wait, Antares on top right there, ice cube, and then LHC. These experiments are basically in that high energy regime where the center of momentum energy of the interaction that you're trying to detect is the 14 TeV. So for example, with LHC, so the LHC center of momentum energy is sort of capped at that 14 TeV. Last time I checked, it could have changed a little bit since then. And then sort of ice cube's center of momentum energy is at that TeV level, where basically EV is electron volt energy unit, and then these letters in front kind of give it a different order of magnitude. So TeV is the 10 to the 12, PeV is 10 to the 15, EeV is 10 to the 18, GeV is 10 to the 9, and such. Okay, so at the bottom here, actually, just in EV, I say what high energy means. It's 10 to the 9 to 10 to the 17 EV. So if you don't like those, other words, GeV, TeV, things like that, you basically have this 10 to the 9 to 10 to the 17 range to tell you where high energy falls, okay? So basically, ultra high energy is even higher. I'll show you the ultra high energy stuff in just a second. You can see a little bit of the ultra high energy off to the side there in the blue boxes, but you can't really see all of it. So high energy experiments are a little bit more common, and also at this point, I would say high energy experiments are important to understand or know about, because we actually have some high energy neutrino discoveries. So I've been mentioning how neutrinos at the high energy and ultra high energy are extremely difficult to detect. They're very elusive. We have detected neutrinos at lower energies, but when you go to those high energies, they're actually kind of very difficult to detect. You get a lot less of them. So when the first few PeV, for example, neutrinos, 10 to the 15 EV neutrinos were first discovered by the IceCube experiment, it was a really, really big deal. And the fact that we started to discover astrophysical neutrinos, so not just neutrinos from like our sun and whatnot, but neutrinos coming from potentially extragalactic astrophysical sources and neutrinos that you could do like astrophysics with. These are in that high energy bracket, and we actually have discovered some of these, many of these now. So that's a tremendous achievement, okay? So here, once again, you have Antares and IceCube. They're both neutrino experiments. Antares is in the Mediterranean Sea, so it's in the northern hemisphere. IceCube is in the South Pole of Antarctica, so it's literally at the South Pole. It's called, it's literally at the South Pole station and closer to the actual South Pole part of Antarctica, whereas, as opposed to my experiment, was actually in a different part of Antarctica. So IceCube, for IceCube work, you would actually go to the South Pole, versus for my work, you would go to a different part of Antarctica. Okay, so those are a couple of well-known neutrino experiments. Especially IceCube is a really that's probably like the number $1 billion world class. I mean, they're all world class experiments, but the most successful one is probably quoted as being IceCube. Okay, and then I have LHC in the same bracket here for the high energy stuff, to just kind of give you a comparison that to give you the comparison of the energy number. So the Large Hadron Collider used to operate at a lower energy, but last time I checked, it can now go up to the 14 TeV range for when they're colliding particles together and things like that. So just to give you a comparison of what the high energy regime means, I'm comparing Antares and IceCube center of momentum energy to the Large Hadron Collider center of momentum energy. So Large Hadron Collider typically is not considered a neutrino experiment. It has a number of experiments in particle physics, but it's not necessarily like a neutrino focused collider or detector. But I wanted to have the LHC on there so that you have another well-known thing to compare to when you consider Antares and IceCube, which are high energy neutrino experiments. And they're both high energy neutrino astrophysics experiments. So both of these experiments are used, and they're observatories. They're astronomy or astrophysics observatories. They're not just particle physics experiments, okay? Then you can see in the two blue boxes, Ascarian Radio Array, or ARA, and Ariana. These are two experiments that are basically the cousin experiments of my experiment. And so that's why I put it here. I actually put a lot of the experiments on this slide because I was trying to point out the different energy regimes in which each of them operate. And Ara and Ariana, so Ascarian Radio Array and Ariana, are also based in Antarctica. And they are both radio experiments to also look at neutrinos. And they're sort of between high energy and ultra high energy. So that's why I positioned them at the point I did. And I'm going to show you the ultra high energy stuff. We have to go over this way with a different screenshot. But the Ascarian Radio Array and Ariana are in between the high energy and ultra high energy. Okay, so pretty much ultra high energy regime is considered to be greater than 10 to the 17 eV. This black thing you see over here is meant to be an arrow that's going this way, but it's cut off in this image. I'll show you the rest of the image here in a second. But those are the two experiments that are sort of the cousin experiments. The blue boxes are sort of the cousin experiments of the ANITA project that I worked on. Okay, so now I will show you the rest of this. Let's see if I can screenshot this part. AirDrop is so nice. But next time I can prepare these to be a little bit better and fitting on the screen better. Okay, so now, okay. Yes, okay. Now you can see, right? Yeah, perfect. So now you can see the ultra high energy regime. So now I've got the ultra high energy experiments here in the purple boxes. So you can see Ascarian Radio Array and Ariana are in the blue boxes because they're sort of in between high energy and ultra high energy. And those are the cousin radio experiments to my experiment, which is ANITA. So I worked on ANITA, the Antarctic Impulsive Transit Antenna. It's an ultra high energy experiment to look for neutrinos or ultra high energy neutrinos. And then a couple other, just to point out. So once again, just to point out a couple other ones that are also in particle physics or astrophysics, and just to compare, is I've named Auger and New Moon. So Auger is actually also an astro particle experiment, but their goals are different. Mostly they look for cosmic rays, and just because a lot of people are, you know, in the what do you call it, in the field. Let me actually Google Auger for you real quick so I can give you a better description of it. Just because some people are more familiar with Auger. It's called the Pierre Auger Observatory, like in more detail. It's an international cosmic ray observatory in Argentina designed to detect ultra high energy cosmic rays. So a lot of people in this field actually work on cosmic ray detection, ultra high energy cosmic ray detection. And so those people might be more familiar with this experiment, Auger, A-U-G-E-R, Pierre Auger Observatory, which I have on here in the slide just to compare it as well. So basically in the same sort of energy regime where Auger operates for the ultra high energy cosmic rays is where my experiment ANITA was operating to discover ultra high energy neutrinos. Turns out that we are actually sensitive to ultra high energy cosmic rays, and we detect those as a, you know, side product, side note, whatever, which is pretty exciting, but it's not our main goal. So that's what this is. This is the ultra high energy regime, which is greater than 45 TeV for center of momentum energy, and the neutrino energy of interest in this bracket would be greater than 10 to the 17 eV or more neutrino energy. But then the center of momentum energy of that interaction would be greater than 45 TeV. So that's the ultra high energy regime. And then just to kind of, just for completeness, if you go to the left of this slide, we have basically less than 10 to the 9 EV, or basically a GeV range or less, are experiments like Hyper K and Dune, which people might have heard of as well. So Hyper K is that's sort of the more normal neutrino energy experiment. Lots of neutrinos from the sun, I believe, for that one. And then Dune is higher energy than the MEV. Dune is more like a GeV scale experiment, I believe, and whatnot. But those experiments, again, very different. So pretty much depending on where in this scale of energy, see how the scale I've been trying to show here with the cartoon is basically showing energy, and you're getting higher and higher this way. So that way is lower and lower energy, and those experiments are very different than the high energy, which are different from the ultra high energy. So that's sort of the fuller picture. And depending on where you are, your experiment will be designed differently, and your neutrinos will be different energy, and your sensitivity will be different, and the physics that you probe with that neutrino will also be different. So that's sort of the fuller picture of this. Hopefully that was somewhat helpful. Yeah, I'm gonna try and do portrait next time. I think you mean try portrait instead of landscape. Yeah, I for some reason I thought that I can move the picture and like toggle it this way and that way, but I guess I can't with the green screens. So I don't know why I thought that. Maybe I can on TikTok, I don't know. So that's why it was difficult here. I thought I can like zoom in and toggle it, and can I? I don't think so. Can I? Yeah, no, I don't think, like for some reason I thought I can move it, but I can't. Acacio! Thank you, Acacio, did a super chat. Wait, I'm trying to like it. The live stream software has been a little funky lately. I don't know why. As in YouTube's side of the live stream stuff has been a little bit not always working. So thank you so much, Acacio. Basically, what was I saying? Yes, Steven, I'm going to try portrait instead of landscape next time. Thank you. Hi, Skeletor. Oh, and Veer had asked, it's just starting point of my career, pursuing my research career. What's your research in, Veer? Big Frank says hi. Hi. Acacio, thank you so much for doing a super chat. I really appreciate you. Thank you. Muchas gracias, amigo. Thank you so much. I've been trying to like your super chat, but it's not letting me. Oh my gosh, Steven. Oh my gosh, Steven, thank you so much for your super chat. Can I like it from here? I think I hearted it. Thank you, guys. Oh my gosh, thank you. And I'm gonna answer your questions. Give me 1 second. Oh yes, I liked it. From my phone, I was able to. It never let me share the live today for some reason. I think YouTube even has a message for me saying that the live stream is like a little bit funny today, or has been for a few days. So Stephen, I believe, asked, what are Antares and Ice Cube? I'll tell you. I think I've said something already, but I'm gonna say again. Sneaky person at work, you hearted me. Thank you. Thank you so much. Big Frank says you're amazing. Oh, thank you. So let's see if it'll let me share it now. I'm just curious, even though it's so late. Hi, Anna. Anna is saying hi, Granny. Hi. I'm the sneaky person, but you hearted me too. Sneaky you. Aw. Big Frank is saying so brilliant. You're getting bald. Should see a doctor. Am I getting bald? Okay. Evil eye remove. Evil eye remove. Thank you, universe, for hair and care. Evil eye remove 222. I love when people join. Thank you so much. And can we get 10 likes? Can we get 10 likes? And 10,000 more super chats from my lovers and haters? And my friends and foe and my fam? Okay, so let me answer. So you already know what the Large Hadron Collider is. I said a lot of stuff while I was pointing to the slide. I can't even remember exactly everything. So let me just say it again. So the reason I was showing you guys the Large Hadron Collider in the green box to the left when I was when I was showing the, oh, you know what? I can go back. That's right. I can go back to the, look at this technology. Once I have the screenshots over here, I can even go back to it. Like and subscribe. Okay, so you already know that the Large Hadron Collider is a very famous detector, of course, Switzerland, France, all that stuff. I've never been, unfortunately. Some people in my field have actually been there and tasted the bread there, so they can tell you better. But I have not experienced the nice bread and the work at the Large Hadron Collider myself personally, because I was in particle astrophysics. The experiments at the Large Hadron Collider are more in the pure particle physics domain, okay? So the people that are smashing things together, the people that are colliding particles with other particles to discover new particles and, blah, blah, blah. Hopefully they discover Susie. Hopefully they discover, that is supersymmetry. Hopefully they discover dark matter or something. The people who discovered the Higgs boson, those types of people, like major particle physics efforts are going on. Major particle physics efforts are going on at the Large Hadron Collider, right here, which operates at an energy which can be expressed in center of momentum terms of 14 TeV or less. Okay, so this is a human-made accelerator. So particle accelerator right here, Large Hadron Collider, human-made on Earth. Okay, this is also something that I bring up when I talk about particle accelerators that are made up, or that are found in nature. So this is a particle accelerator right here, the Large Hadron Collider, made by us, made by humans. But actually, particle accelerators can also exist in nature, in certain very extreme environments of nature, such as gamma ray bursts, such as what happens when there is some extra big supernovae from some stars dying, or from neutron star, or black hole mergers. So those types of things can also create environments of extreme particle acceleration, which can also do particle physics of its own. And that's why it's important to probe astrophysics, or that's why it's important to probe those types of environments in nature and have astrophysical means in our hands as well. So this Large Hadron Collider is a human-made particle accelerator. We're trying to do our own controlled particle physics experiments and discoveries and things like that there. But there is a bunch of things happening in nature already that are also important to probe in addition to this work. Okay? Like, for example, gamma ray bursts. This is a transient event in the sky that can happen. It's a very extreme one, and it's very luminous. Remember, it was like for the brief period of time when a gamma ray burst is, doing its thing, emitting radiation, it can be the brightest thing. It can outshine a whole galaxy in luminosity. So those types of extreme events are also particle accelerators, and there's a lot of physics to be unearthed from there as well and understood from those things as well. And how do we do that? We should try to detect particles and detect signatures and things from those types of sources. And so for that, we have experiments like Antares and IceCube and the ultra high energy experiments as well, like what I was working on, Anita, Ara, Ariana, things like that. Auger, because basically the prediction is that there are theoretical predictions for both cosmic rays and neutrinos coming out of such big astrophysical events. And if we can successfully detect the particles that come out of these types of events, then we can probe those events. There would be not too many ways to probe them otherwise. We can see the light from them sometimes. Hopefully, a lot of the time, every time that we see a neutrino from a thing, it would be good also if we saw a light from that same thing, and then it would be like a multi-messenger astronomy situation, or a gravitational wave from the same thing, stuff like that. But pretty much just like it's important to study particle physics in the Large Hadron Collider, it's also important to study astrophysics and particle physics that happens at actual, real, natural astrophysical sites. And that is why these experiments exist. So Antares is a neutrino experiment looking for neutrinos from astrophysical sources. IceCube is also a neutrino experiment looking for neutrinos from astrophysical sources. And they're looking for neutrinos of high energy, as in between 10 to the 9 and 10 to the 17 eV neutrinos is what they're looking for. Antares is in the Mediterranean Sea. It utilizes the Mediterranean seawater to detect neutrinos. Let me actually Google that real quick. I hope I didn't say that wrong. It's a lesser known experiment, but it is known, and it is a thing. First neutrino telescope in seawater. I was right, guys. Mediterranean. It's in Mediterranean. Let me read out to you what is Antares. 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 I worked on Anita, right? Do you know why I take all this time to talk about the other experiments first? Because you have to. Because you have to know what is in the overall field. And you don't want to make people mad. Okay. I'm on the Antares website now. Antares, can you just tell us what you are real quick? Ugh. This website has too many things going on. Oh, I'll just tell you. So it uses the it uses the Mediterranean sea water as a detection medium for the neutrinos to interact in and produce an optical signature that it will catch with PMTs. The same sort of thing, but some differences in the details, is done by IceCube, but using ice in Antarctica at the South Pole Station near the actual geographical South Pole of this planet. Okay? That's what Antares and IceCube are. They're both astrophysical neutrino hunting experiments and detectors, and they have both successfully actually discovered and measured astrophysical neutrinos, which is a pretty big deal. Within the last decade or so. This is new. This is not an old field. Astrophysics, or not astrophysics, particle astrophysics is like a 20-year-old field, maybe like 15, 20 at the most, unless I'm counting wrong. But like when I was doing it, it was like a 10-year-old field or something, you know, it was new. With neutrinos. With neutrinos, it was pretty new, within 10, 15 years old. So you might not have heard about Antares and IceCube, but at this point they are well-established experiments and they're quite successful. And they have actually detected high-energy astrophysical neutrinos, as in neutrinos that come from astrophysical sources, extragalactic phenomena that are really cool and have a lot of energy. Okay. Cherenkov. They look for the Cherenkov radiation emitted from neutrino interaction in a medium. And Antares and IceCube look for optical Cherenkov signature. My experiment looks for radio Cherenkov signature. Okay, does that help? Hi. Hello, my grass is greenest. Astronomy fan. Yes, please do like, share, and subscribe. Thank you for being here. Thank ya. Okay, so Antares, let me tell you the full form of it. I didn't even know this is the full form. Oh my gosh. Please do like, share, and subscribe. Thank you so much. Tell all your cousins and neighbors about this channel and about this live and about our videos and shorts. Please do keep on watching and keep on coming to the lives and see our shorts and videos and sending your comments. I read them first thing when I wake up. So please do send your comments. Thank you so much. Thank you, universe. And let us know your questions and ideas and things like that. So Antares is astronomy. So by the way, in the field, everybody is like crazy about acronyms. And so Antares is astronomy. Are you serious? The A is astronomy. Astronomy with a neutrino telescope and abyss environmental research project. Honestly, I didn't know that that was what it stood for. I knew the name Antares. Thankfully, IceCube is just IceCube. They literally mean a cubic kilometer of ice in Antarctica. IceCube, I believe and I hope, and I'm not going to check it because I don't want to be shocked, but IceCube, this experiment, IceCube, very important experiment right here, might be the most important experiment in neutrino astronomy, neutrino astronomical observatory, neutrino astroparticle physics experiment. Right here, $1 billion experiment. Right here is a cubic kilometer of actual ice cube at the South Pole Station of Antarctica, okay? Which is, by the way, a high altitude place. Where? Fun fact, Buzz Aldrin, that's a guy, right? That's the name, right? Steven, second guy on the moon or something. He went there same time as when I was there, as in when I was in Antarctica, and he got very sick. I hope he's okay now. I mean, I hope he got okay very quickly. But you do get high altitude sickness if you go to this ice cube place and you're not careful, because the South Pole is not only the South Pole, bottom of the Earth, but it is also very high. Did you know that the bottom of this Earth is very high indeed? So be careful. Be careful when you go there. Drink wawa and don't do a lot of exercise. Drink some Gatorade. But also I think it's like hard to breathe and stuff, so there's that. I didn't go to the South Pole. I went to Antarctica in a different spot. Not at the South Pole. Not at the very crazy high altitude place. But my friend did, and he was fine, so it's not that bad. Okay, so Antares is the thing I said, astronomy with the whatever. Neutrino detector residing 2.5 kilometers. So by the way, this is the fun facts. 2.5, so it resides 2.5 kilometers under the Mediterranean Sea off the coast of Toulon, France. Oh, yeah, okay, makes sense. So food might be good if you work in this experiment. It is designed to be used as a directional neutrino telescope to locate and observe neutrino flux from cosmic origins, like I was saying, astrophysical origins, in the direction of the southern hemisphere of the Earth. Wait, if I'm Antares. Oh. Maybe they are expecting to see the neutrinos that go through the Earth from the southern sky. Huh. Oh, yeah. Okay. That's cool. I forgot about that. So, from cosmic origins in the direction of the southern hemisphere of the Earth, a complement to the South Pole neutrino detector ice cube that detects neutrinos from both hemispheres. So ice cube detects neutrinos from both hemispheres. If you have one that detects neutrinos from one hemisphere, then it can actually serve as a very good check of the other experiment. So this is why it's important to have complementary experiments. The experiment is a recognized CERN experiment. Other neutrino telescopes designed for use in the nearby area include the Greek Nestor telescope and the Italian Nemo telescope, which are both in early design stages. The data taking of Antares. So Antares is kind of done with its data taking. Doesn't mean that it's done because they still have to analyze the data and publish and all that stuff, but it looks like the data taking of Antares was finished in February 2022. So 2022, 3 years ago. So they're probably still like analyzing, publishing, and coming out with the outputs. But it was operating for 16 years before they kind of wrapped it up, and probably will upgrade and have other experiments deployed. The array contains a set of 12 separate vertical strings of photomultiplier tubes. Each one has 75 optical modules and is about 350 meters long. Actually, I don't know why I'm reading the Wikipedia page, because I also have this in my thesis, but it's okay. Wikipedia is fine too. They're anchored at the bottom of the sea at a depth of about 2.5 kilometers, roughly 70 meters apart from each other. When neutrinos enter the southern hemisphere of the Earth, they usually continue traveling directly through it. On rare occasions, a few muon neutrinos interact with the water in the Mediterranean Sea. When this happens, they produce a high energy muon. So muon is a lepton, remember, one of the leptons. So this is the secondary particle that it would make once it interacts in the water. Oh yeah, high energy muon. Antares works by its photomultiplier tubes detecting the Cherenkov radiation emitted as the muon passes through the water. The detection techniques used discriminate between the signature of upward going muons, a muon neutrino that has had interactions with matter below the detector, the Earth, and much higher flux of downward atmospheric muons, because we also have atmospheric muons. Fun fact. In contrast to the South Pole neutrino telescopes Amanda and IceCube, so there's another one, Amanda, that I didn't mention earlier. Antares uses water instead of ice as its Cherenkov medium, as light in water is less scattered than in ice. This results in a better resolving power. So that's the detection medium they use is the seawater. In Antarctica, the ones that are based in Antarctica, there's a lot more in Antarctica, because a lot of the experiments like ice as the detection medium. So the ones in Antarctica, obviously they all use ice as the detection medium. Okay, let me see. I will share some more visuals with you guys next time, and I'll try to make it portrait. Oh, good. Stephen mentioned he landed on the moon with Neil Armstrong. Armstrong was second man to step. Okay. He also went to Antarctica at the same time as me. And he got sick, unfortunately. But a lot of people do, so it's not rare. Okay, so hopefully today's discussion of the experiments was, you know, a good introduction to some of this material that belongs to the particle astro world. We will talk more about these things next time. I'll try to make it so that I can kind of show you how the neutrinos like interact and whatnot. Like what exactly happens. Like basically the neutrino will actually hit a quark in the medium because it's coming in with such high momentum. And it's really from that a particle shower develops and we get this Cherenkov radiation. So there's a lot of details in this work that I didn't talk about today. I was just pointing out some basic information, some of these other experiments that are in the same field and whatnot to give you sort of a broader overview. And hopefully I made the point about the energy regime and how that kind of affects things and where the experiments are, what they're trying to do, etc. So hopefully that was helpful, and thank you everybody for watching and listening. And if you're seeing this later on, please do like, share, subscribe, and please do share your comments and messages with us in the chat or in the comments, and continue to see our videos and clips and shorts. Thank you all so much. I think I'll wrap it up. Any last comments? Let me know. And Thank you for the super chats, everybody. Steven and Acacio, thank you. Heart, heart, and heart. Yes, heart. And I will prepare these as portrait images next time. Hopefully that helps tremendously with this issue. Okay. Thank you, everybody, and see you next time. Bye-bye. Any last comments? Let me know. Bye. How do I make this go away? Here, I'll share it.